Hello everyone, I'm Hongbo Zhang from National Institute of Applied Science in Hua. Thank you for viewing my presentation. Today, I'd like to share my recent research in time-variant reliability-based optimization with double-loop Kriging surrogates with you. First of all, what is time-variant reliability? It is an analysis that allows capturing the time dependence of the probability of failure and the uncertainty of the deterioration process. The assessment of time-variant reliability of existing substructure is subjected to degradation is an important task for taking decisions on inspection, maintenance, and repair actions. The time-variant reliability-based design optimization, shortly for TvRBDO, approach aims at searching the optimal design that minimizes the structure cost and to ensure a target reliability level during the operational life. There are two main kinds of time-variant reliability methods. First of all, it is called the outcrossing method, which is defined as an event of performance function passing through a failure threshold. The outcrossing methods are based on Rice formula that the distribution of outcrossing is a substitute for the Poisson's distribution. Next is called the extreme value-based method, which is tries to evaluate the performance function at the maximum value of each trajectory of the random variables through time. In most cases, there is no analytic solution for the extreme value of the performance functions, so it will become prohibitive for engineering problems. In this case, surrogate models are often used. However, there are many inconveniences of these methods. For example, mixed EGO, which is shortly for mixed efficient global optimization method, uses double loop Kriging, with inner loop represents the performance function and the outer loop represents the extreme value of the inner loop. The double loop Kriging of EGO method will amplify the error in the inner loop, and it is computationally expensive to identify new training points. To overcome this kind of problem, a single loop Kriging surrogate methods, shortly for Silk, is proposed. Generally speaking, in Silk, the time interval is discretized into small time steps at each threading design variable and uses a learning function U to decide whether to update the inner Kriging or not lose track of the random variable. The fundamental idea of Silk is to build a surrogate model. Here we use Kriging models to evaluate the problem. To make sure the surrogate model is accurate for the classification, a U criterion is used, which is defined as this formula. In this research, the limit for U is set to bigger than 2.5, which means the probability of making an error is smaller than 0.62%. If the surrogate fails to find an accurate point, that the G is greater than 0. In this case, we think that the points are needed to be updated by the Kriging. The updating points are decided by searching all the random X by minimizing X and UT for each time steps. Lastly, the stop criterion for the updating is that the maximum prediction error is lower than a limit value. In this research, we use 5% as the limit. The maximum prediction error is given by this formula. Here, the F1 is the number of samples for all random variables X and time steps T that satisfies our criteria described in the previous slide. Now comes to combine the time-variant reliability with the design optimization with Silk method. To combine these methods, we are firstly to construct two separated Kriging surrogates. The inner loop Kriging is used to calculate the TVR, time-variant reliability with Silk method, and the outer loop Kriging is used to conduct the TvRBDO. After the outer loop Kriging is built, the expected phasor function, shortly for EFF function, is used to update the Kriging. The EFH is this function is given as this formula. So the first step is to build an inner Kriging that is drawn by sample uniformly from the bound for variables. Then we will draw Latin hypercube sampling for the design variables x for design space delta d. Then we will calculate the vector of failure rate PF related to Silk method. Next step is to build the outer Kriging with x and the failure rate P coming from the last step. Then we need to update the outer Kriging by maximize the EFF function mentioned in the previous slide. The EFF function update stops when the maximum EFF is smaller than a criteria. There we fix it at this is 10 minor, that is smaller enough, and the maximum number of samples are added. Then we conduct optimizations using the outer Kriging and the optimum design and added it into the outer Kriging dataset in step 4. The last step is that the optimization stops when the change of the optimum design is lower than an error. Here we use the 5% as mentioned before. Now I will give you some examples and results to validate this method. The first example is a numerical example that consists in two random variables, x1 and x2. The design variables are the mean value of the two variables. The time interval for this problem is said to be between 0 and 5. The option function and constraints are summarized as below. The named failure rate P is set to be 0.4 for all probability constraints. The performance functions are given as the following. Here is a figure that illustrates the three performance functions with different time instance. And here we compare the proposed method to NERS method, which is a method based on the extreme value of the double loop EGO time variable reliability method. We can see that here the proposed method TRDLK consumes less function evaluations compared to the referenced method. These advantages come from the Silk. The TRDLK method used here, it uses more function evaluations and iterations to converge, but compared with the referenced method, it should be noticed that after the outer loop Kriging is built, the computational cost for the proposed method is minimum. Another example is a two-bar frame structure subject to stochastic force Ft as shown in the figure. The two distances of O1, O3, and O1, O2 are random variables denoted as L1 and L2. Failure occurs when the maximum stress in either bars are larger than their material yield stress S1 and S2. The design variables are the diameter of the two bars D1 and D2. The distribution parameters of the random variables are listed in the table below. So the stochastic force Ft is considered as a stationary Gaussian process with exponential square autocorrelation function given by this function. The mean value and standard deviation of Gaussian process are stationary as mu f equals to 2.2 and mu f equals to 2.0 multiplied 10 square 5. The objective function is given as in this function, and the limit failure rate P star for two performance functions are said to be 0.01 and 0.01. So here is our final result. As shown from the result, we can see that the proposed method T consumes less function evaluations than the referenced method given in the NERS. So we can have the same conclusion as the previous example. To conclude, in this research, a double loop Kriging surrogate method is proposed to conduct a time-variant reliability optimization. This method consists of two separate Kriging surrogates. The inner loop Kriging evaluates the time-variant reliabilities using silk method, and the outer loop Kriging is trained with the result from the inner loop. After the out loop Kriging is built, it is then updated with the EFF functions at a lowerable failure rate. Two examples are used to validate the effectiveness of the method compared to the other existing method. This method is simple, accurate, and easy to implement. The computational cost mainly comes from the searching of points to upload the inner Kriging. After the outer Kriging is built, the computational cost for optimization will be minimum. However, due to Kriging is less competent for high linear problems and high dimensional problems, this method may less effective for such problems. Also, the inner loop Kriging error will be accumulated to outer loop Kriging. It is recommended to use smaller coefficient of variation value. This will inevitably increase the total consumption cost. Thank you for your attention.